Greetings. In this one I'll be showing how to take the inverse of a 2 by 2 matrix. So let's get into it. First of all, I'll show what the 2 by 2 matrix means. So basically 2 by 2 matrix is such a matrix that has 4 entries. It has 2 entries, it has 2 rows and 2 columns. And let's say that the 4 entries, as a matter of scheme, I will call them A, B, C, D, A, B, C, and D. And the first thing to determine about this matrix is if it's invertible or not, because I'm talking about the inverse of the matrix. So let's say that this matrix I'm taking, this is the most common name for matrix, that's capital A. So let's say that this matrix, I call it capital A. And then I want to find this so-called A to the minus 1, which is the way to denote the inverse of this matrix A. Alright, so it is the same kind of notation as would be with numbers, let's say, but in this case, of course, in making the inverse, taking the inverse of a matrix is slightly more complicated. Although with this simpler 2 by 2 one only, it's quite fast. Alright, so let's get into it. And first of all, I'll just show the very basic property of an inverse of a matrix. So the idea basically is the same like with numbers. Let's say one has 1 over 2 and 2. Well, that is the same like 2 times 2 to the minus 1. 2 to the minus 1 is the 1/2, right? And these together, when multiplied, they give 1. And the idea, the corresponding idea among matrices here is the identity matrix, which it can have different amounts of columns and rows. In general, nicely definable for square matrices. That means the same amount of columns and same amount of rows as here, for example, 2 by 2. And so let's say it is the matrices where one has diagonally down from the top left corner to the bottom right corner once, and all other entries are zeros. Alright, so this is a 3 by 3 one, but I could also show it for the 2 by 2 one. It's called the identity matrix, denoted as I. So let's say for the 2 by 2 one, well, it will be as follows. Alright, so this matrix is the identity matrix, and it's kind of the thing that represents the idea of taking the inverse of the number and multiplying it by the number itself to get 1. So with matrices, one gets the identity matrix when matrix is multiplied by its own inverse. Alright, so that will be the goal, that we have some matrix with 4 numbers. A, B, C, D will be numbers. I will use integers for simplicity, and actually I won't use 0, just to make it as clear as possible, although 0 won't make it not that clear. But anyway, I'm taking 4 entries like this, 2 by 2 matrix, as I mentioned, and I want to find a matrix, another one, that if I multiply this matrix by that one that is the inverse of A, right? So this one is A, and if I get the inverse of A, well, I want this concrete property that this matrix times this A to the minus 1, so this is the order reverse, but this matrix multiplied by whatever I will find to be its inverse, which will be this A to the minus 1, will together be equal to the identity matrix of however many rows there are and columns. Well, in this case, it is 2, so there should be a subscript of 2 here, but I'm not doing it just for simplicity. I'm just writing I might go into those subscripts later in another one. But anyway, the idea is that I have a 2 by 2 matrix, and what I want is whatever numbers are here, I want to multiply by another matrix, so that when I multiply, the resulting matrix will be 1 and 1 here, otherwise 0. So 1 and 1 diagonally, the top left corner and the bottom right corner, like this. Alright? So identity matrix, so the inverse matrix, what it does is it multiplies the initial matrix, and the result of this multiplication matrix will be this identity one, which I've shown how it looks. It just got 1s here and 0s here. Alright, so that's it. And let's say now I want to find out the method to do it. So I'll give a concrete example, or maybe first, before doing so, I can write the formula. There actually is a concrete formula for it, and the idea is as follows. When this is the initial matrix, I'm taking the inverse matrix. Well, the formula for getting that matrix is as follows: 1 over AD minus CD. Alright, so that's this times this minus this times this. And then I take the same matrix, but what I do is I switch the order of these two, so it's D here and A here. I switch them, and then I multiply these two by -1. So I give these two the minus sign, or whatever sign they had in. Previously, I will invert that sign. And this will be the result as the inverse to this matrix. Alright? And also this shows the nice thing, by the way, this AB minus CB, it's the determinant, it's called the determinant. I've gone into this earlier on, and the point is basically the determinant is this time this minus this time this, which is exactly what it shows, AB minus CB in such a matrix with these letters, representing the 4 entries it has. And by the way, the invertibility of a matrix, the possibility for it to be given an inverse, is enabled by the fact that AB minus CB is not equal to 0. If it was, it would be dividing by 0 here. So according to algebra, it would be incorrect. And also 0 equaling to AB minus CB in such a matrix shows that it's not possible to take the inverse of that matrix. It's not possible to invert, or in other words, it's not an invertible matrix. Alright, so this is the way we're going to do it. So let's say that my A will be 1, 2, 3, 4. 1, 2, 3, 4. So what will be the inverse matrix? Well, I can follow this rule. So it's A to the minus 1 should be 1 over, and this is a constant multiple which will multiply each of the 4 entries here. So AB minus CB, well, there's this minus this, so it's 4 minus 6, so it's minus 2. So 1 times 4 minus 3 times 2, so 4 minus 6 minus 2 in here, alright? And I just take the AB CB, whatever their values are here. And then this one, well, as the scheme shows, this was A, B, C, D. I'll just write it here once again, A, B, C, D. In parentheses, just to remember which ones were which. And what I do first is I switch these two, so D and A are switched. That means that 4 goes here and 1 goes here. And then these two, their signs are inverted. So it's -3 and -2, as follows. So this is the result, this is the inverse matrix to the initial A. And also this -1/2, here in front of the matrix, I can put it into each of the entries. I can multiply by this constant multiple each entry of the 4 in this matrix. So I can do it straight away. This was the scheme, I'll delete it for now because it's already been shown. And there's not much space to put my further calculations. So A to the -1, which is the indication of the inverse of the matrix A. Well, that will be this thing, multiplied by this constant multiple. So I will take each entry, and when multiply constant multiple, well, each of these 4 entries will be multiplied by it. So it's -2, this becomes 1, this becomes not that nice, 3 over 2, but still quite good. And this becomes exactly what the multiple was, because this is 1. Alright, so this is the result. And now I can check it. Now I can check it for correctness via a matrix multiplication. Alright? But yeah, I might do it actually, the matrix multiplication, even in this video. It's possible that I will do it right now. Alright, so I can get straight into it. I might have also done matrix multiplication in another video, but I might do a different method of doing it, or maybe a quicker way of doing it for another video. But now I'll show here exactly that it indeed turns out to work the way it should have. So when I multiply by this initial matrix, by the inverse matrix, as I've stated, it is expected to be equal to 1, 0, 1 here and 0, as follows. Will it be so? Well, the way to multiply two matrices, this is one matrix, this is the second one. How to multiply two matrices, by the way, I'll write it here so to get more space. It's as follows. And again, as I just mentioned, there's no way to approach it, but I'll show the more general, short, slower, more concrete, or more easy not to get lost in a way. And the idea is basically I take this first matrix, so let's say I multiply this one by this one. I can also do it the other way around, but I will choose to use this one as the one, because I will do A times A inverse instead of A inverse times A. So when I do A times A inverse, what I do is I take this matrix, which is 1, 2, 3, 4, and I first multiply by just the first column of the second matrix that I'm multiplying by. So what this gives is basically I use -2 as the multiplier for this column and this for this one. Now doing it a little bit quicker, basically this times this plus this times this, and put it into the first entry of the vector. And then this times this plus this times this, put it into the bottom entry of the same vector. So it's -2, -4, that's the first entry. Actually, this won't be 2 entries, this is going to just add up, this is going to be one number. And then, or actually this is -2 times 2 times 3 halves, that's 3. So it's going to be actually plus 3. And the bottom entry is 3 times -2, that's -6. Plus 4 times 3 over 2, which is 6. Alright, so what this should be is 1 and 0. So this is the first column, alright? And once I've done the first column of the second one, well, I again take the first matrix that I'm using in the multiplication. So again, I'll just separate this. So this is 1, 2, 3, 4. 1, 2, 3, 4. And now I'll multiply by the second column. And after I do so, I will use this as the first column of the matrix that will be the result of the multiplication. And the second result I'm doing right here will be the second column. And it already shows that indeed it turns out being correct so far. Alright, so I'm taking the second column of the second matrix, 1 and -1 half. So if I apply the same process again, create the vector as follows. It's 1, -1, so it's 0. Nice, that's what I expected. And 3 and 4, that's 3 minus 2. So this is going to be 1. So indeed this ends up being 0 and 1 in total. 0 and 1. Right, this is a vector. Alright, so what I do now is I put these two vectors next to each other into a single matrix. So the result of this entire multiplication is indeed I got 1 and 0 and 0 and 1. So indeed this is right. Then the result of the multiplication is 1, 0, 0, 1. And this proves exactly the beginning point, which was when two matrices are multiplied where one is the inverse of the other, then the result will be the identity matrix. And this is exactly what we got.